Hello, I'm Jisoo Lee from Korea University, and today I'm going to present VidChain, chain of tasks with metric-based direct preference optimization for dense video captioning, which has been accepted at AAAI 2025. Dense video captioning is a challenging task that has gained significant attention as video continues to grow longer in length. And the goal of DVC is to generate a concise video story that supports human comprehension without having the viewers to watch the entire video. So specifically, given a long unterm video, the model needs to understand the major events, determining how many segments the video can break down into. Then the model should localize those events within the video by providing timestamps for each. And finally, the model needs to generate a caption for each event. As a result, DVC is a challenging task that requires to identify which part of the video or events are critical to provide a concise summary. Recently, the rapid advancement of large language models has spurred the integration into video understanding tasks, giving rise to video large language models. And these models have shown impressive capabilities in tasks like video question answering and captioning, leveraging the visual information. However, when it comes to fine-grained temporal video understanding, which often relies on long unterm video and require multiple video-related subtasks like dense video captioning, these video large language models have shown unsatisfactory performance. Video large language models fall short in fine-grained temporal video understanding, especially in DVC, for two key reasons. First, the conventional approach in dense video captioning relies on one-step reasoning. So given a single instruction prompt, the model predicts both the description and the timestamps for all events in a single step, despite the complexity of the tests. And as a result, the model fails to fully utilize its reasoning capabilities, often predicting an overly large number of events with repetitive captions for each one. Second, the gap between the training objectives and evaluation metrics for DVC often results in suboptimal performance. In dense video captioning, models are evaluated using a combination of metrics. So for example, caption quality is measured by the METEO, while the timestamp accuracy is assessed using the intersection over union IOU. And the SOTA, which is the major metric of DVC, integrates these metrics through dynamic programming to provide a comprehensive evaluation. However, video large language models are typically trained with the next token prediction, a simplistic objective that does not fully reflect the complex evaluation protocol. Hence, first we've introduced co-tasks that decompose the objective of the challenging task into a sequence of subtask objectives. So in specific, the objective of DVC, which is to predict, given a video, the number of segments, the timestamps, and captions, we can decompose the objective into two different chain of objectives, as shown in A and B, which we refer to as two different reasoning paths. In terms of the reasoning path B, the model is prompted to first generate the number of segments the video breaks down into, then the model is expected to generate the captions for each event, and lastly, the model is expected to localize those events within the video with timestamps forming a multi-turn conversation. And we specifically trained the model by building system benchmarks into a multi-turn conversation involving both reasoning paths to reason in a co-task manner. For the inference process can also follow one of the two reasoning paths, which we just simply prompt the model with the path-specific prompts as shown. To address the second problem of misalignment between training objectives and complex evaluation metrics, we can further train the model under supervision by the evaluation metrics for each task of co-tasks. But in fact, directly incorporating such metrics into training is quite challenging. To handle such challenge, we introduce metric-based direct preference optimization, MDPO, where we learn the metric preferences, that is, the preference derived from evaluation metrics for a subtask that composes co-tasks. The idea of direct preference optimization is to align large language models' output with the human preferences, and it aims to train the model to increase the likelihood of the preferred response relative to that of the dispreferred response, given the prompt X and the video for multimodal domain. Inspired by such DPO, we present MDPO that aligns the video LLM with the metric preferences, where the evaluation metrics for the subtasks with cotasks is adopted as a criteria to determine the preferred and dispreferred responses. And this approach allows to supervise the metric preferences on the final response of the model, as well as the intermediate subtasks that allow for more fine-grained supervision, and also reduces reliance on human annotators being cost-efficient. Furthermore, a key advantage of metric preferences is that the metric evaluations go beyond standard binary decision datasets by incorporating continuous labels. In other words, metric preferences reveals how much the output is preferred, which we can optimize the model with such continuous preferences, especially accounting for the preference gap. So we train the model on sample pairs where the difference in evaluation metrics between the preferred and dispreferred responses exceeds a certain threshold, facilitating the learning process. Overall, aligning the model with code-test and MDPO, the VidChain enhances the video LLM's fine-grained temporal understanding where the generated results for the given video closely matches the ground truths. Here is the main results on dense video captioning tasks. The main results reveals that VidChain applied to two state-of-the-art video LLMs, VTime LLM and Video Llama 2, outperforms all other across different metrics and across different benchmarks, ActivityNet and Youku 2. Also, as shown in the ablation study of the components of VidChain, Codetext and MDPO consistently enhances performance across all video LLMs and benchmarks. Moreover, we analyzed different variants of DPO objectives, and the results underscored the effectiveness of MDPO. We observed that optimizing the model with intermediate tasks from codetests, while being preference gap aware, accounting how much the sample is preferred, achieves the best performance. In conclusion, we present code-test that leverages the strong reasoning capabilities of the model to address dense video captioning, and then we introduce MDPO that provides supervision for each intermediate task and integrates the continuous nature of the metric with metric-based DPO. Overall, VidChain is an effective framework that is generally applicable, improving the fine-grained video understanding capabilities of video LLMs. Thank you for listening.